Okay.
All right, so the stage is all yours. So
Okay,
please go
thank
ahead.
you.
Perfect.
Well, first of all, I wanted to thank the organization and all the staff that makes this possible, and thank you for inviting us into this presentation and this congress. It's a great opportunity for us, and it's just a thanks for you. Well, basically, nice to be here. I'm Adrian, CEO of Curious Space, and today I'm going to present you what we think that is the future of the space, which is the very low Earth orbits. Just to start a bit from the beginning, who am I? I'm currently the CEO of Curious Space, but I have my background in aerospace engineering. I did my master's in aerospace engineer here in Spain, in Barcelona. Such a nice city, by the way. Feel free to visit it whenever you want. And I also did my master's in management in Grenfell University in the UK, where I complemented all my knowledge in aerospace together with the management skills needed to bring a company or a startup such as the Curious Space. Aside from that, I also did my first startup when I was 17 years old. I have always loved the entrepreneurship and bringing in new projects that bring new knowledge to the humanity, I would like to say. And I also took my part of my studies in the Northwestern University in Chicago. A bit briefing also from Crazy Space. We just founded the company in 2021, 6 founders, all of us in the same college doing the aerospace engineering, but all of us also specialized in all the different areas, as I just said, in management. We have been growing since then. We just made this project as a follow-up from an European project, Horizon, in which my university took part together with some other universities, which was the Discover project. At the moment, we grew to now 9 employees. We have raised over 20,000 euros in private and public funding, and 2 of our team members are also PhD students. Well, now going to matter, what brought us here is the very low Earth orbits. It's an unknown term at the moment, or just few people in the sector know about it, but even time more and more people is talking about this. Very low Earth orbits are considered any orbit between 100 to 450 kilometers. I would say less than that, to 350 kilometers, since over that current propulsion systems can overcome the drag pretty easily. So I would define it as any orbit in the range between 100, where space starts, to 350 kilometers. At the moment, it's a pretty unexploited orbit, since most of the satellites are operating in the low Earth orbits with the big constellations that we already know, such as Starlink, and the ones that are appearing now, such as OneWeb or any others. This very low Earth orbit has such different characteristics than the found in the lower Earth orbits and in the current satellite missions that are done. One of them, for example, is that there's no need for any kind of end-of-life system for those satellites, since the atmospheric drag that's found in those very low Earth orbits, the orbit the satellites just automatically as soon as the propulsion system is turned off. This is a huge benefit in comparison with the current missions, since we are able to reduce the space trash generation by a lot. Since any crash, any thing that goes out of the mission design does not have any kind of long-term effects to the orbits and to the space segment. Also, well, the space trash lag also enables easier operations in orbit, which reduces the amount of propellant needed for that kind of debris avoidance maneuvers and other kind of maneuvers related to these things. And it's also really uncrowded, which also allows for new places for the constellations to be set up. Also, a big important benefit of going to those very low Earth orbits is the reduction in the UV radiation that the satellites get, and the decrease in the effect that this has in all the all the circuits that are integrated into the satellite, amplifying the lifetime of all those subsystems. Well, why do we think that very low Earth orbits are the future? Well, basically because since we are able to orbit closer to the Earth, we are able to provide an impact in the resolution for both telecommunications and Earth observation. When it comes to the Earth observation, we're able to provide up to 3 times better resolution for optical payloads, thermal payloads, and hyperspectral payloads. Here is just an example, and this has lots of applications when it comes to maritime, to when it comes to agriculture several systems. And then when it comes to SAR systems, we are also able to reduce the power that they need. So reducing the amount of solar panels that are needed and the weight of the overall satellite. This is a huge impact for missions for different companies such as ICEYE or other companies operating SAR satellites at the moment. And this could also reduce the costs of those missions. And when it comes to telecommunications, we have seen the interest that the industry has in these very low Earth orbits. I'll explain this later on. But we are also able to improve the data rates up to a 300% in comparison with the current orbits. This is just using the same satellite, just reducing the altitudes, and we're able to reduce the latency by a 60%, which has also huge applications when we want to transmit lots of data really fast. This might be a niche application when it comes to these improvements, but when we go deeper when we dive deeper on the benefit it has, we also see that the reduction in the cost and in the launch cost, which is up to, we are able to launch with the same rocket up to 65% more payload. The reduction in cost also appeals for lots of different segments than just the niche ones that might be benefit of this. Also, what we have seen is a reduction in the average altitude of satellites. This has been driven by the apparition of these new constellations in low Earth orbit, such as Starlink, such as the one that Satellogic is doing, and lots of others. But we have seen that this reduction has been of 14 times in just 5 years. And at the moment, it has been established at 1,000 kilometers, more or less, altitude. But the industry has the need of reducing the average altitude and the orbits in which their satellites are established. So basically, we see that this trend is really clear, but there are now limitations that avoid that the satellites could be established lower. Also, we have seen that the industry has really been going into those very low Earth orbits, although they have been unexploited at the moment. We see that Starlink started at 1,000 kilometers, then they reduced it to 550 kilometers, and they saw that they could even get more benefit by going even lower. So they are launching their satellites now at 350 kilometers, although they are struggling a lot to make the scheme sets that they are doing, since they have a lot of restrictions in terms of shape, and they need a lot of propellant to maintain those satellites in orbit. Also, we have seen here in Europe, this might take you a bit over or far from the US, but we have had the GOCHE mission, which was the first real mission into the very low Earth orbits. It was at 200 kilometers, and it was used to measure the electromagnetic spectrum of the Earth electromagnetic field. And this allowed to demonstrate, it used a kind of propellant that was electro thruster, but it was used to demonstrate the viability of establishing satellites in those very low Earth orbits. It didn't remain too much. The mission that has lasted the most in very low Earth orbits is one, as I said previously, the orbits below Starlink. It has been less than 2 years, so it's pretty low, but it has demonstrated that it can be done. At the moment, it can just be done by scientific research, which does not really appeal to the commercial market, which is the real one. But at the end of the day, demonstrates the interest that there is. Also, we have seen Albedo, among others. There have been other startups interested into doing constellations in very low Earth orbit, but Albedo it's a huge one. It just raised 50 million euros for their constellation in $50 million for their constellation in very low Earth orbits, and they have been pioneers in introducing this kind of orbits or this kind of maneuvers into the market. So they are reaching 10 centimeters resolution imaging just by getting into the very low Earth orbits, which is their main value proposition. This has a lot of applications, but the most appealing ones for the industry are from the part of the Earth observation, the precision agriculture, since we are able to really monitorize the fields and the crop really precisely and get lots of information just by using a satellite instead of using drones that are really expensive to be used every day in that huge amount of fields. When it comes to maritime, it's also a great application, since we are able to really follow the boats and the ships, and to know which ship are we monitoring precisely, even though we don't have the exact data of it. Also, when it comes to homeland security, forestry to detect wildfires, it's a great tool as well. And the obvious response is defense. We are also able to get really good and quality data for defense applications. And when it comes to telecommunications, the broadband, since we are able to provide a better and faster communications, and the IoT applications that come for planes, for example, or other IoT specific applications that might benefit of this, and also the fast communications that come from defense. Now, the question is obvious: if we are able to provide that much benefit just by reducing the orbit without any need to increase the payload or any need to increase the size of the satellite, why it's so hard to be done? Well, there are basically two main issues into going to the very low Earth orbits. The first all and the most important one is the aerodynamic drag caused by the remaining atmosphere. When we go higher, the atmospheric pressure and density is way lower. But when we go to 200 kilometers, we're finding drags in the range of hundreds of millinewtons that make the satellites fall really fast. Just to get an idea, the satellites in 600 kilometers would last over 10 years in orbit without any kind of propulsion system. In fact, in those orbits, those propulsion systems are used for other kind of things, or other maneuverings, orbital plane changes, and that kind of things. But when we go to 200 kilometers, the time that satellite would last is just a matter of days. So the missions that would be commercially interesting in those areas are completely unviable. And in the case that we use the current propulsion systems to overcome this aerodynamic drag, the cost could rocket up to 5,000% more, which makes those missions completely unviable in economic terms. That's why most of the missions done in those 200 kilometers range have been done for scientific purposes, not for real commercial missions. And we also find another problem, which is the atomic oxygen. That is a component which composes most of the atmosphere in those altitudes. It's over 70% of the composition of the atmosphere in 200 kilometers, and it's a really corrosive element for the exposed parts of the satellite, which also limits a lot the materials that can be used or can be used to coat the satellite. Those two problems can be solved not easily, but can be solved with one same solution, which is the air-breathing electric propulsion system. That's exactly what Crazy Space has been doing during these 2 years, 5 if we take into account the European program. That consists of a technology that propels the satellite just by using the remaining atmospheric air and solar energy, without needing to carry any kind of propellant on board. This allows us to reduce the size of the satellite and to maintain the satellites in orbit for over 5 years without any kind of propellant. Also, it's really important to highlight that our system prevents the satellite to be corroded by the atmospheric atomic oxygen that I was talking before, since we cover all the part that could be harmed by this atmospheric composition by the air intake, which is the part that takes all the atmospheric air and brings it into the propulsion system. It's also an eco-friendly technology, and at the moment we are in TRL 3. We have been doing tests. In fact, we have been the first company in Europe to do a testing of the air intake. We did that in the only facility in Europe that allows to do so, that allows to simulate a relevant environment, which is the Von Karman Institute. And we have also tested the plasma thruster, which is basically based in an Helicon thruster. This is because we are able to generate plasma without needing to be in touch with that corrosive environment. That allows us to have longer lifespans and also to reduce the damages produced to the propulsion system due to this element. I would also like to talk about a use case which might be interesting. We have done our calculus not just for Earth observation, but also for telecommunications. But this one I think is pretty interesting for lots of use cases. That would be that for a 300 kilogram satellite with the current technologies for Earth observation, and by applying just a bit of artificial intelligence, which is already being applied, we would be able to obtain an 8 centimeter GSD by a panchromatic, by a panchromatic imaging. This could be done without needing to carry any kind of propellant, by reducing 4 times the weight of the satellite that would be needed in higher orbits to obtain the same imaging, and also reducing the cost up to 3 times in comparison with the current technologies. This will allow lots of different applications, will enable not just the very low Earth orbit, but all the applications that will come up from there. We will make a space ahead from lots of other technologies, such as the high altitude balloons, or even the drones, or in ground testing, since we will be able to cover lots of different areas by just using one satellite at the same precision that we could be doing just with a hub. This is really impressive when it comes to a change that it will take into the space industry and all the applications it will have. And when, well, I just showed the Earth observation use case, but it also has an impact for telecommunications, as I just said. If we were able to bring Starlink, for example, to 200 kilometers, the benefits would be awesome. The problem is that at the moment, there's no propulsion system that allows them to do so. So that's basically it. It's also important to note that, because I think that you might ask that as well, the reduction in swath and the reduction in revisit time is something to be noted. But when you do the calculus of this use case by reducing the swath, we also see that the economic impact of a constellation would be really great, reducing to a half the cost of doing that constellation for the same coverage, the same revisit time, and with the same resolution, which is also impressive. These calculations have been done for different aspects as well. When we have done it for defense, for example, for the war that's being fought now in Ukraine, also for all the agriculture of France, and all the results have been validated with those use cases. So, well, basically that's it. If you have any questions, I will be pleased to answer you. And you can also contact me to any of those contact points. Thank you very much.
Wonderful. So thank you again, Adrian. So I would just like to remind the audience that they are able to connect with you as well, because I'm going to drop a link that they will be able to use to request a private meeting with you as well, to discuss the business or other networking options and the other propositions that they might have. But now, moving into the questions, we have quite a few here from the audience to you. So Adrian, one of the questions from the audience is you're using, again, electric propulsion. The question is, will nuclear energy or plasma be a possibility for a technology similar to this? So that's a question to you.
Okay, we are using plasma, in fact. So it's, of course, plasma will be the solution, we think, for this, because chemical propulsion for this kind of satellites might be too heavy and might not make much more sense. There have been studies on that, on using the atomic oxygen to be used as chemical propellant, but you also have to carry some part of the combustion there. And when it comes to nuclear, we think that the propellant that you need to bring, or the nuclear paste that you need to use there, might be too heavy for this. Anyways, I don't discard it. It might be an option, but we think that nuclear makes more sense for interstellar programs.
Awesome. Okay. Perfect. So then the next question is from the audience, as I'm looking here right now. The next question is, will you be able to manage re-entry location if air density increases suddenly? So that's a question for Mikhail.
That's a thing to be taken into account. The density in very low Earth orbits is really variable. It changes a lot depending on the location and the sun, well, how strong the sun is at the moment. So it's something to take into account. We have been working in a GNSS that will be implemented into the satellite that takes into account those atmospheric variances. So we should be able to really control the satellite in that deorbit process, even though the satellite will need to be designed to be integrated into the re-entry maneuver. So in the case we lose the control of the satellite it shouldn't be any problem. It will be certified that this won't be any problem in the case we lose this control.
Perfect. Okay, so then a question from my side to you, Adrian. So initially, what urged you to come up again with this solution for the air breathing propulsion?
Well, it was because there are several factors that just show that this is the path forward. The first of all was the trend of the space sector that is fulfilling all the available orbits in LEO with huge constellations, massive constellations, and they need other places to be used. This is the first and foremost. Also, the trend that we see that we need better resolutions to make use of the satellite data. And the best way to do it is by reducing the orbit instead of just increasing the prices and increasing the cost of the satellite missions. This might be cheaper and more usable. And why air breathing? Because it's the most, it's the idea that fits the most with the idea of staying in very low Earth orbits recurrently and viably, economically. There are two of them, two main views on that, the skim sets and the air breathing electric propulsion. What we see is the skim sets really restrict a lot the satellite, also bringing a lot of propellant on board, which also increment the cost and don't really take everything that could be taken from the very low Earth orbits. They might work in higher altitudes, such as doing with the SpaceX, but when we really want to take profit of those very low Earth orbits, we need to go for an air breathing.
Absolutely, makes sense. There's another question from Jean Javid. He's asking if you see the same technology for the attitude control system or only for the main engine of the satellite.
It might work for all the different operations that need to be done in a satellite operation, but the main one is orbital keeping. But we could also use it for those kind of small maneuvers that could be done.
Perfect. And then a question from my side. So in the future, what new developments or breakthroughs in air breathing systems do you envision, and how would they help with the main goal of the, again, satellites in low Earth orbit, enabling the lowest orbits?
Well, there are lots of breakthrough technologies that need to be developed in the field of air breathing electric propulsion. In fact, there are several technologies being developed at the same time with different scopes, trying to adapt holes, using the Helicon as we are doing. There are several opportunities in that. A main one is in the terms of materials, to really understand the materials. If we are able to get a material that reflects the particles of the flow specularly, we would be able to double the efficiency of the thrusters, which would be awesome. That would really increase the viability of this kind of systems, and also materials that allow for longer durability of the thruster and all the satellite against that atomic oxygen as well.
Perfect. And another question again from my side is that what are some of the current limitations with the air breathing systems that you're facing?
Well, basically the efficiency of the thruster. It's really hard to get the right fit into thrust to drag ratio, and also to fit it into the power requirements for the satellite operators, because we would be able to make a satellite or a thruster that gives a really good thrust to drag ratio, but the amount of power that it might require might not fit into the platform requirements that the industry is now asking for. So getting that optimized is the most challenging part of the design.
Perfect. Amazing. Okay. So I think that's the main questions here. So let me check once again if there's any additional questions in the chat. So there was Thomas with a more generic question. He was asking if the bigger high resolution cameras would be able to provide the same quality imaging from higher altitudes. So what would be your take on that?
Well, we just improved the resolution of the cameras. It's not that if they are better, we are not able to improve it. We are able to do so. The SWAT might be smaller, but we are also able to increase the resolution up to 3 times. So even though they are able to get a 15 centimeter resolution in 600 kilometers, we would be able to get a 5-centimeter resolution in 200 kilometers.
Perfect. So it's just more efficient, makes more sense in terms of the usage of the cameras as well, that you would need lower resolution camera would make even a better, higher quality imagery. That would be amazing. I mean, that's very, very innovative, Adrian, and I'm sure there's a lot of uses for that already from what you discussed. We see that. So definitely we will be following your journey, Adrian, and for the audience as well. So I encourage them to reach out to you. So I will drop this link here once again, that people will be able to connect with you and request a private meeting to discuss the potential business opportunities and just networking and collaboration. So please make sure to reach out to Adrian. Yeah, on this, I think we can conclude the session, Adrian, unless you want to add anything from your side, because we got a few.
Just that. Okay. Feel free to get in touch with me. I will be pleased to answer any question you have.